in level 49, we saw that the solubility is favored if the solute and solvent have similar properties. So for example, we can compare a fat-soluble versus a water-soluble vitamin in the picture. So in A, which this is pictured on 518 in your textbook if you'd like to look at it more, A shows us a nonpolar fat-soluble molecule, which is vitamin A. We know that it's polar because of the hydroxide groups. The more hydroxides that you have, that makes it more polar, okay? Versus vitamin C, which is picture B, and it shows you from the chemical structure that there's a bunch more hydroxide or OH groups there. So that means that it's more polar than the nonpolar fat-soluble molecule. So like dissolves like, remember, so water would dissolve the vitamin C a lot better than the vitamin A because there's more polar bonds on vitamin C. Some factors that also affect the solubility, another one is pressure. Pressure does little to change the solubilities of solids or liquids, but it does have a large effect on the solubility of a gas. So carbonated beverages are bottled at high pressures to ensure the high concentration of the CO2 in the liquid to create the fizzing when the container is opened. And so this picture is on 519, but it's showing how with a gaseous solute in an equilibrium for A, but then as you create less volume by pushing in the piston for B, that creates a higher pressure of the gas. This causes the rate at which the gas enters the solution to increase, so the concentration of the gas increases when it's dissolved in the solution. Then for C, it's showing that you are having a greater gas concentration in the solution causes an increase in the rate of escape. So a new equilibrium is then formed when you create a different volume and create a different pressure. Henry's law shows the relationship between gas pressure and the concentration of dissolved gas, where C is the concentration of the dissolved gas. K is the constant, and it's characterized for a particular solution. And then P is the partial pressure of the solute, the gaseous solute above the solution. Henry's law states that the amount of a gas dissolved in the solution is directly proportional to the pressure of the gas about the solution. So for example 3, a certain soft drink is bottled so that a bottle at 25 degrees Celsius room temperature contains carbon dioxide gas at a pressure of 5 atmospheres over the liquid. Assuming that the partial pressure of carbon dioxide in the atmosphere is 4 times 10 to the negative 4th atmospheres, calculate the equilibrium concentrations of carbon dioxide in the soda both before and after the bottle is opened. The Henry's law constant is 3.1 times 10 to the negative 2nd moles per liters atmospheres. Okay, so we are going to solve 2 of the equation, the C, and it's going to be of the CO2. So when I put the little CO2 there, it's just telling what it's of. So for the Henry's law, concentration is equal to the constant for carbon dioxide times the partial pressure of the carbon dioxide. Okay, we know the constant, they tell us in this little weird copy and paste mumbo jumbo, is 3.1 times 10 to the negative 2nd moles per liters atmospheres. And that's just so that we cancel out the pressure when we multiply by it. Okay, so for the unopened bottle, we know that the partial pressure of the liquid is 5 atmospheres. So that is going to be our partial pressure of the carbon dioxide. Okay, so to solve for our concentration of carbon dioxide in the soda, we would just take the constant, 3.1 times 10 to the negative 2nd, times our 5 atmospheres, and that gives us a concentration of 0.16 moles per liter, and I already rounded to sig figs just to make things quick and easy. Okay, so that's one of our answers. That's for the unopened can. Now let's figure out the concentration when it is opened. Okay, well, that we have partial pressure in the atmosphere is, in that weird mumbo jumbo, 4.0 times 10 to the negative 4 atmospheres. So that's going to be our new partial pressure of the carbon dioxide. So then plugging in a separate equation to solve for the concentration using the same constant, 3.1 times 10 to the negative second, times that partial pressure. The concentration is 1.2 times 10 to the negative fifth. Your calculator might have given it as a decimal, and that's okay. Well, so that's our other answer. This means, just so you guys know, that to compare these two numbers, since we've done the before it's opened and the after it's opened, the concentration of the carbon dioxide is much greater before it's opened than after it's opened. And that is showing us, that's showing us the reason why your pop will go flat. Because when it's opened and the carbon dioxide is free to leave the container, it will leave the solution, or it will leave the soda, and so then that's why the pop gets flat, and you're just left with everything else in the solution, and the gas has then been gone, and so there's no more fizzing. So that's just a real kind of real world example for this. Temperature can also have an effect on the aqueous solution. This graph is pictured on page 520 in your textbook, but the dissolving of a solid occurs more rapidly at higher temperatures, but the amount of the solid that can be dissolved may increase or decrease with increasing temperature. So predicting the temperature dependence of solubility is very difficult. The only way to ensure or to determine the temperature dependence is by experiment. And so I do this sometimes when I have to make a really concentrated solution in a really short amount of time. I might heat up the solution to aid in the solubility to dissolve the solid, because temperature does help with that. And so this graph is showing you the differences in temperature as you go across the x-axis and the solubility. So some things actually decrease in solubility when you heat up. The sodium sulfate and the cesium sulfate do that, or the cerium sulfate, excuse me. But most other things will increase in solubility as the temperature increases. The behavior of gases is very different. It appears to be less complex than the solids. The solubility of a gas in water typically decreases with increasing temperature, and this actually does have environmental impacts like thermal pollution that it talks about on page 520 in your textbook, also a boiler scale and other things that are also talked about there. So check that out for more information on the environmental impacts of the temperature with gases. So now we're going to talk about the vapor pressure of solutions. Liquid solutions have physical properties significantly different from those of a pure solvent. So this is a picture of a closed system. It's in a bell jar, it's closed up, where it's showing that the vapor pressure of the water, which is the pure solvent, versus an aqueous solution. So the solvent in the aqueous solution is the water. Okay, well, the vapor pressure of the water is higher than the vapor pressure of the solution because the solute particles are holding down the solvent, so it's having a harder time to turn into a gas. So then B is showing that the solution will absorb the water molecules that are trying to escape the pure solvent, and after they turn into gaseous form, and they're going to be condensed back down into the aqueous solution. So after a period of time, the water is transferred to the aqueous solution, which actually makes the concentration diluted, so it's not as concentrated anymore. But this is just showing us how the vapor pressure, the pure vapor pressure of a pure solvent is less than when it's in solution. So a non-volatile solute lowers the vapor pressure of the solvent because it's trapped in there with that solute. The dissolved non-volatile solute decreases the number of solvent molecules per unit volume, and it should be proportionally lower than the escaping tendency of the solvent molecules. So we have Raoult's law for this. I like saying Raoult. P solution is the observed vapor pressure of the solution. The X solvent is the mole fraction of the solvent, so that would be the moles of the solvent over the total moles of the solution. And then the P solvent with the 0 is the vapor pressure of the pure solvent. Okay, so we can use this equation to solve for the P solution, or the vapor pressure of the pure solvent, anything like that. Note that for a solution of half solute and half solvent, the mole fraction is going to be half, 0.5. So the vapor pressure of the solution is half that of the pure solvent. That's just something that you could know, but if you don't remember that, you can always just solve for the mole fraction and then figure that out later. So we're going to do example 4 to use this equation first. But I do want to point out that the solute is always the thing given with less. If you can't determine necessarily what the solute is, it's going to be whatever has less involved in the solution than what has more involved in the solution. Okay? So we're going to kind of see that, and you're going to notice that in your work examples and all that kind of stuff. But it's the one with less. Okay, for example 4, we want to calculate the expected vapor pressure at 25 degrees Celsius for a solution prepared by dissolving 158 grams of table sugar, which I give you a mole mass, that's nice, in 643.5 centimeters of water. At 25 degrees Celsius, the density of water is 0.9971 grams per cubic centimeter, and the vapor pressure is 23.76 torr. So, that's a lot of information, okay? What we're using, we have dissolving sugar in water, okay? So that's telling us that our solute, just so we can think about it correctly, the solute is going to be the sugar, and the solvent is going to be the water. Okay, just so we can get our heads wrapped around that. Also, for the sugar, we have 158 grams versus the water, we have 643.5 cubic centimeters. And if it's very, very close for the density of 1 to 1 for that, that would be 643.5-ish grams. Okay? So that's, I just wanted to point that out. Okay? So for our equation, when we're solving, we're going to be solving for the P solution, the pressure of the solution, for the, and so we're going to have to plug in the mole fraction of the water, because that's the solvent, times the pure vapor pressure of the water. Which, it tells us right here that the pure vapor pressure of the water is 23.76 torr. Okay, so we're just going to have to solve for the mole fraction in order to get the observed vapor pressure of the solution. Okay, so let's convert our grams to moles for the sugar first. So the 158.0 grams of the sugar over 1, and we're going to divide by the molar mass, which I give you in the problem is 342.3 grams. So the moles of sugar is 0.4616, and I just rounded to 4 decimal places, or 4 seconds for now, just because. So that's the moles of the sugar. Okay, for the water it's going to be a little bit more involved, because we're going to use the cubic centimeters and the density given to get grams, and then we have to go to moles. Okay, so I'm just going to do it all in one step. Alright, so then we have our 643.5 cubic centimeters over 1. I'm going to multiply by the density, 0.9971, because that's grams per 1 cubic centimeter. So that will help us to cancel out the cubic centimeters. And then we are going to divide, just like we did before, by the molar mass of water, which the molar mass of water is about 18.015 grams. So when you solve that out, you get that the moles of water are 35.60. Okay, So then next, we need to solve for the mole fraction of the water, where we take the moles of the water, so the 35.60, over the total moles. So we're going to take the sugar moles plus the water moles. So the mole fraction of the water is equal to, when you solve that out, 0.9873. So then we can use that mole fraction and the pure solvent vapor pressure to solve for the P solution. So it's going to be the mole fraction, 0.9873, times 23.76. So the observed vapor pressure of the solution is 23.46. And I'm going to put torr because the pure solvent's vapor pressure was in torr. All right? Not too bad. Okay? We're going to do example 5 now because it's a little bit different. In example 5, we're using an ionic compound instead of using a molecular compound like sugar. Okay? And so when you have an ionic compound, you have to take into account the number of ions that are dissolved or are present when it is dissolved. Okay? So we're still going to be using our P solution. So let's figure out, I guess, what's our solvent and what's our solute. So the predicted vapor pressure solution prepared by mixing 35 grams of solid sodium sulfate, which I gave you the molar mass, with 175 grams of water. The vapor pressure of pure water is at 25 degrees Celsius is still the 23.76 torr. Okay? Well, we have 35 grams of the sodium sulfate versus 175 grams of the water. The solute is going to be the sodium sulfate, okay, and the solvent is still going to be water. Because we have 35 grams of the sodium sulfate versus 175 grams of the water. There's less sodium sulfate, so that's the solute. Okay? So our P solution equation is still going to look the same. The mole fraction of water times the pure vapor pressure of the water. So we still know that the pure vapor pressure of water is 23.76 torr. Okay. So we need to convert from grams to moles to figure out the new mole fraction. Okay. So for the sodium sulfate, 35.0 grams, divide by the molar mass given, which is 142.05. And I got those moles to be 0.246 moles of the sodium sulfate. Okay. And then for this water, 175 grams divided by the same molar mass we used in example 4, 18.015. Make life easy. So the moles of the water this time are 9.71. We didn't have to do that whole density thing because it was already given in grams. It wasn't given in a volume unit. So that's why we didn't have to do that here. Okay? But before we solve for the mole fraction, this is where it gets a little bit different. When you dissolve an ionic compound in solution, like we saw in one of our homework problems for 49, you have multiple ions that are dissolved. So sodium sulfate is made up from 2 sodium ions and 1 sulfate ion. So that's a total of 3 ions, okay? So the actual concentration, or the actual number of moles of the ions in there is going to be 3 times of what you would just solve for, because it creates those 3 ions. So the moles of the ions are 3 times the number of moles of the solute dissolved. So that means, since there's 3 ions, because there's 2 NAs versus 1 SO4, so a total of 3, we're going to take the moles that we just solved for times 3. And that's going to give us the moles of the solute more specifically. So taking that times 3, it's actually 0.738 moles. okay? So that's the number that we're going to plug into our mole fraction for the water. So we're still going to have the moles of the water on top, the 9.71. But now we're going to take the 9.71 plus our new moles of the solute, the 0.738. So the mole fraction for the water now is 0.929. And so then the P solution our pure vapor pressure of the water, which is 23.76, is 22.1, and I ran into 3 sig figs from our original problem tour. Okay, you will have a couple of these on the assignment, so ask me if you need help. Sometimes it might be multiplied by 2 if it's just like sodium chloride or something like that, but you have to pay attention to what your solute is. Alright, we're almost finished. Non-ideal solutions do come into play. So far the solute has been assumed to be non-volatile, so it doesn't contribute to the vapor pressure. But for liquid-liquid solutions, it can be quite different. Because if you have a liquid dissolving in another liquid, then both liquids can create vapor pressure. So the total pressure here is equal to the partial pressures of each liquid. So a PA, PV, partial pressures of each liquid, where the partial pressures are equal to the mole fraction times the pure vapor pressure of each liquid. Okay? So make sure that you know what that means. Okay? So this is when you have 2 liquids together. That's really important to remember. A liquid-liquid solution that obeys Raoult's law is called an ideal solution. It's an ideal solution just like an ideal gas is an ideal gas. Okay? So the table I have here is the summary of different solutions and the behavior of them. So the part on the left where it shows the interactive forces between solute A and solvent B particles, that's going to be important to know if something's actually going to dissolve in something else. Like, because sometimes if like dissolves like, then it will work out fine, but other times it will not. Okay, so that's on page 526 in your textbook, and if you need some more reading on this information, look on that area. Okay, but we're going to do example 6 where we have 2 liquids combining together, but we have to figure out which one's a solute and which one's a solvent by figuring out which one has less and which one has more. The one thing I want to do before I switch over to the other page to do the example is, in your note packet, it is not written correctly. Here on the screen, it is written correctly now. So I had a typo and I lost a bunch of information in your notes, but it has been fixed for future generations, but for this year, it's not. So make sure that if it's not correct in your notes, that you take a second, pause, and write everything down correctly. So for example 6, a solution is prepared by mixing 5.81 grams of acetone and 11.9 grams of chloroform together. At 35 degrees Celsius, this solution has a total vapor pressure of 260 torr. Is this an ideal solution? The vapor pressures of the pure solution, or the pure liquids, are 345 and 293 torr respectively. Okay, so let's gather our information so then we can figure out which is the solvent and which is the solute. Okay, so I'm going to say A for acetone and C for chloroform. For acetone, we have 5.81 grams given, and for the chloroform, we have 11.9 grams. Well, right away, just looking at this, the acetone has less. So the acetone is really going to be our solute, and the chloroform is going to be our solvent. Okay? Other information. We know the pure vapor pressures of each. So the pure vapor pressure of the acetone is equal to 345 torr. And the pure vapor pressure of the chloroform is 293 torr. So the whole question about is this an ideal solution, and it gives us the 260 torr. We are actually going to solve for the total pressure, and if it's equal to 260, then it will be in fact an ideal solution. If it's not, then it won't be an ideal solution, and then we could figure out if it's a deviation of a positive or negative from Raoult's law. Okay? So we're going to need to figure out mole fractions. To save time, because this is a long video, I'm just going to go ahead and tell you that because the molar masses are very equal, or equal to almost, when you solve for the moles of each of them, it's 0.1 moles-ish for both, when you take the mass divided by the molar mass. Okay, so because of that, because they're equal amounts of moles, the mole fraction of each is actually going to be 0.5. Because if you solve for 1 to be 0.5, then you can subtract the other one from 1, because mole fractions all add up to 1, you know, like percentages add up to 100. And so both mole fractions will be 0.5 to save us some time. Okay? So now let's plug into our p totals to figure out if this is ideal. So for the acetone, I'm going to take the 0.5 mole fraction times the pure vapor pressure of 345 torr plus the half mole fraction of the chloroform times its pure vapor pressure of 293. So the P total, when you solve this out, is equal to 319 torr. Well, 319 torr does not equal the 260. Okay? It's actually greater than the 260 that it said. If it was equal to it, it would be ideal. So there is a deviation where it's greater than, so it would have a positive or a positive deviation from Raoult's law. And that's kind of from the table that's up above in your note packet. Okay. So this is the end of 50. Thank you for bearing along with me. I know this is a lot of examples. But work on the homework problems, check your checklist to see what you have to do.